Hello, I'm Roman. Welcome back to a series of the videos of building the convolutional neural networks from scratch. The series is based on the previous one, which was called Neural Networks from Scratch in the Golang, where I took the book of building neural networks from scratch in Python, but I implemented everything with the Golang. And right now, using the same code base that we had from that series, I want to build the convolutional neural network. Specifically, in the previous series, I ended up building the. In the previous series, I built a model that can predict the type of the cloth based on the fashionist dataset. And with the convolutional neural network, at first I will do the same, but using the different architecture, or specifically different types of the layers, the convolutional, MaxPool, flatten, so all of the things I need to use the convolutions to solve the same problem. And then we can actually compare the results. I think in the previous one, the accuracy was about very close to 90%, which I guess is a good result for the model that consists from, 3 fully connected layers. And it's not optimized for working with the images. But with the convolutions, the idea of the convolutional layer is that it can be optimized to find the specific features on the images, and then those features can actually be used for categorization. I think, yeah, so this is like what we'll have. This is what we've built in the previous series. So this is the few fully connected or dense layers, and we're going to build the convolutions with feature maps and the pooling layer. And in the previous video, I actually started to implement the layer itself. Right now I have the convolution as the operation. So you can see right now this one. So this is the operation itself. Right, it's a rather small, so it just takes the input and in the kernel, and it returns dense again, so it outputs the result. And I started to build the layer. And the first thing I actually stuck last time is to understand how I'm going to store the data. And I want to actually draw this time. We have an iPad. Let me take a look if you can see. Okay, so how I stored, if we take a look at the forward method, so the forward method actually takes the inputs, and it should create the output at least in the dense layer. It worked like this. So we had an input, and then as the result will produce some output, and that output looked like this. So there is an output. So there is an output of the dense layer. It is a two-dimensional array, meaning that so each row represents a single sample. So for example, this each row represents, the number of the rows represents the sample count. For example, if we take a look at the train methods, what we're actually doing is we take in the batch, which is it actually slices the data in the specific way. So for example, if I want to train on several thousand of the images, we will do training in the epochs. And well, I mean, I want to do several epochs, and each epoch is divided into kind of sub steps. So for example, right now I have the training step here as 1, default value of the batch size is nil. Okay, and if we pass the batch size, then we calculate the training step. For example, for this one, we have, I think here, yes, we have a batch size of 128 images. So it means that for the dense layer, that would be, so that would be here. And this is the image. Well, actually, for the output, it's not actually an image. So this is the output neurons for the layer, and I'm thinking how to structure this for the convolutional layer, because for example, for the dense layer, for example, if the input was an image, so for example, if an input was an image, like for example, that was still 128, but with the number of the columns. For example, if we take a look at the, I think this one. For example, this is the first layer, and if I take a look at the initialization, we have the number of the inputs, which is the size of the image, and we have the number of the neurons. So for example, in the output, this one, so in the output that we have here, we will have 128 by 128 neurons, right? And then, for example, we're passing it into some activation function, and it can go one after another and, well, do the activation. The problem that I have with the convolutions is that the output is actually of the forward method is not a single, for example, for one image, it's not like one corresponding output, it's actually several outputs, right? So for example, if we take a look, that we have the same input data, right? And we have the output shape, but if you take a look at how the output shape is defined, it's a three-dimensional array, right? It's kind of similar to the filter shape. So we have the number of the filters with the filter size. So for example, if we have 3 filters, different filters, or actually kernels, if we had 3 different kernels, that will be 3 by the size of the kernel. Each kernel is a 2-dimensional one, and the output is the same. So for one single input image, we actually will have 3, for example, or num kernels size, where every element of the 3-dimensional array is a 2-dimensional array with the result of convolution between the input data and the kernel. So for example, it means that, for example, if I will have so for example, imagine that I have 3 kernels, right? So for example, this is my input. I have 128 lines. I have 128 lines, or I mean images in the single input, where every row represents an image. And actually this is the grayscale image. I'm still figuring out what to do with the RGB images, but for now I will, I will ignore this fact. So then, for example, I have the 3 kernels, which means that for example, for every input, I need to multiply it for the kernel. And that's, I mean, the interesting part is what should be the result. Check it. Okay. And I'm thinking kind of what I can do is the output. Actually here I can represent each row as a big array that contains all of the kernels of the specific size. What do I mean? I can represent it like this. I could have the 3, like have a big array of the values that will contain all of the kernel, all of the all the results of the convolution between the input data and the output. But still, I mean, and in order to process it next, it means that, for example, in the MaxPool layer, I guess, I need to somehow no, I'm still, I mean, what I'm thinking, for example, it could work with the MaxPool layer, right? Because the MaxPool, where we have, so what for the person in the MaxPool? Okay, so MaxPooling is a simple kind of the pooling function that selectively passes the maximum values from each window to subsequent layer. For constructing the MaxPool layer, we need to specify the pool size, which is the window where the pooling is applied. The pool size, and basically we shrinking the data. So for example, iterating all of the channels. Well, we don't have channels actually. But where it takes the channels? Where it takes the channels? Okay, assuming that's oh, num channels input height, input width. Okay, so it's actually not the number of the channels. I think in this case, if we use the convolution and then pooling, that will be a number of the kernels and then size, but determine the output shape. So that's basically the same. The only difference is the output height and width, because we're going to shrink the size, because, okay, looping through the height, looping through the width. We have the starting position, okay, ending position, okay, and then we creating a patch from the input data. well, patches in terms of the GoNum, I mean this is the slice, right? And find the maximum value from, and we assigning it. So for example, for example, the pool size is 2, so we will have to pick up the max number from the 4 values, and it will give us 1. And this is the pooling. But in the given code, we have multiple kernels resulting in the multiple feature maps. To handle this, we need 3 nested loops. Okay, within each iteration, we create a patch by extracting the relevant section of the input data using the calculated indexes. Then for each patch, we identify the maximum value. By repeating this process for each patch in every feature map, we populate the output with the maximum. Okay, finally, the output feature map, which has undergone the MaxPooling operation, is returned as the result. Okay, backwards, let's skip it for now. I mean, I understand how it will work, because for example, we can, I mean, yes and no, right? Okay, so how it works for the pooling, what is the C? Okay, so it, if pool size, C. Okay, so the output will be actually, I will have, for example, for the pooling, it means that, for example, if I have 3 kernels, that the pooling will work separately for each of the kernel. And then, for example, it can return into something like this. For example, if this was the result of the convolution, then what we can do next? Right, so this is what I can do. So after the pooling, I can go over all of the kernels and do the max pooling, like for each part of the output from the convolution, and then I will create a new matrix where again every line will contain all of the results from the convolution passed through the max pooling. But I still have doubt for this. In the given code, we have multiple kernels resulting in the multiple feature maps. To handle this, we need 3. I read this, okay. Then they actually can build in the fully connected dense layer. We have this size of the input coming, we have it. Size of the output producing. Basically, this is actually the size is the number of the neurons we'll use, and we have weights and biases. Okay, I don't. They have the softmax. Okay, but how the final model? There is a forward pass. I actually don't like. I mean, I like the previous approach better, even in the Python, that the activation function is the different type of the layer that just goes after. You can skip it if you want, but it gives you the flexibility of building and switching easily. For example, see, you can see here, they kind of go in pair. So I have the dense layer, then I have the one type of the activation. Here is the same, and for example, here I have the softmax activation. So I think this is better than hard coding a specific function that does it. And here they actually have to encode, like hard code the backward pass for the softmax activation too. And they consider the dense layer. Category percentage loss and its derivative we have it. So, okay. So the approach, okay, so the model actually looks like this. So they have the convolution. They take a shape from just in X-ray and 0, so they take in the shape of the image and pass it to the convolution, which means that there is an input shape, right? Okay, but they assume that it's a grayscale because there is no RGB channels. I mean, if it's, for example, if the input shape, if it has to work with the RGB image, it should have 3 dimensions. But this one assumes working with the grayscale only. Okay, so then 6 and 1. And what are the params? Okay, filter size and filter number. Okay, so they actually have the filter size by 6 and 1 filter only of kernel. And what they do? Okay, so they have the output of the convolution. Then they use the pool. Okay, and then they use the dense layer, and then they calculate the loss. And then they convert to one-hot encoding, and that basically just to calculate the cross entropy loss gradient. Okay. Predict function, basically the same. Perform classification. Okay. The next thing is more or less clear for me. Well, first, I mean, this is the good start point, but it doesn't fit in the architecture in the approach that they used before. Well, first, it kind of assumes that, well, I mean, actually, my approach that I've been thinking, it will only work, I guess, with the, how to call it? It will only work properly with when there is one convolution and then there is a MaxPooling and then goes everything else. But is it actually common to have convolution of the convolution? I think in one of the examples there were an example of such architecture. Okay, yeah, so for example, there is a convolution 9 by 9 by 1, the input layer 1. Then there is a hidden layer with the MaxPooling. So this is the result of the convolution. You see that there is 1, 2, 3, 4 feature maps. I guess there are 4 kernels. Then you have the MaxPooling that reduces the size of the feature map. And then 10 by 10. 1, 2, 3, 4, 5, 6, 7, 8. So then they double it somehow. Again, MaxPooling. And then they use 25 inputs for the dense layer, and then they can do the classification. So with the approach that I'm thinking, this architecture is not possible, or at least I don't know how to structure it. Really. Because I'm not sure how to adapt this dynamic dynamically increased size of the input within the layer. So this is, consider it as one layer that has actually kind of 4 layers within, and then it kind of just expands further. So I'm not sure. On the other hand, I don't have better approach really. run convolutionals in your browser. So for example, here. Okay, so actually this input. But I've been thinking, what if the input image would be not the grayscale image, actually image that kind of consists from the 3 inputs, right? And I mean, how they... So there is one convolution. I guess it's the 10 kernels, right? For example, let's take a look at the first convolutional layer in a tiny VDG architecture. Notice there are 10 neurons in this, 10 neurons, but only 3 neurons in the previous layer. I'm trying to understand how they add up all intermediate results and then add a bias. Oh, okay. So they have one kernel, right? And they use RGB as... So they use the same kernel, right? Click here. Wait. So there is... Okay, this is actually what I'm going to think on. Currently it was the brainstorming. I still thinking how to properly structure it, because I mean, for sure I can build something like this, because here they actually hard-coded, for example, they hard-coded the way that you access the convolution, then you access the MaxPool, then you have the Fulk. But I mean, it's not the same that I have here. For example, in the model train, in the model, actually model forward, I had some like this. So I just taken the output from the previous layer and passing it to the next one, and it should work. And the reason that the layers is actually just an interface. It's just an interface. It has the get outputs and the input. Well, the input is used for the backward path, but the main thing is the get output. I might thinking that I will have to pass some metadata about the previous layer to the next one. For example, I can allocate, I can instantiate the convolution and return some, for example, the output size or something else from the init method. So I can pass it to the MaxPooling and use this. And with the, the reference to the dense in the row, I will have all of the data all at once, and then it's, I can split it inside the layer based on the output and the additional information that I passed during the initialization, which should be okay. The only thing I'm trying to understand is how to support multiple consecutive convolutions, one after another. One convolution, MaxPooling, convolution, MaxPooling. So how I structure all of this. So this is what I will think. Maybe I will find out something tomorrow. Maybe you will tell me. That's an option too. So there is no code today, and it's actually pretty late, as I didn't manage to start recording earlier, but at least I get more or less an understanding how I can fit it into the current code base and the current code structure, so I can use it. And at least for sure, I can build the convolution. I can build the code with the assumption that there's only one convolution and one MaxPooling, and then it just goes several dense layers. That will work for sure, and that I can implement like already tomorrow. But I will see if I'm going to think about it more, or I will go with the building it for the grayscale and then changing it to adapt for multiple convolutions. So for now, thank you for watching, and see you tomorrow. Bye bye.